All right, so just to introduce myself, my name is Ritwik. I am a junior at Arizona State University studying aerospace engineering. And recently this summer, I'm also a member, well, currently I'm also a member of our university's amateur radio club, Whiskey 7 Alpha Sierra Uniform, W7 ASU. And this summer I've also become a licensed ham operator, KO6 EUF, in case you guys are interested in contacting me. I was thinking about putting it here, but I wasn't sure what the etiquette was about that part. But yeah, I just wanted to let you guys know because I noticed a lot of that. But anyway, to introduce a bit of the work that I've done the last semester or spring 2024, me and one of my professors, Dr. Daniel Jacobs, we worked on designing a guidance system for the completely hackable amateur radio telescope. So to give you a bit of background onto the rationale behind why I decided to do that. So currently, there's quite a bit of there's a lot of discussion on astronomy, or at least the very basics of it in elementary through high school. But the problem with that discussion, at least, is that it's not quite as in depth as it could be. A lot of people, when they think of astronomy, they just think of the optical side of things. And although people mention the electromagnetic spectrum and that visible light is a part of that, along with radio waves, there's not really much of a discussion onto radio astronomy itself. And a lot of the times, if anyone does see a mention of radio astronomy, it's in pop culture to some extent. Like what was it? There was that movie where I believe it was a VLA that was featured in it. Um, I forget the name, but things like that. That's usually how people get into the hobby. The prop, but the whole, but in order to fix that issue, a lot of different organizations have been coming up with their own versions of radio telescopes, cheaper ones than the VLA, like the completely hackable amateur radio telescope, Bharat, Salsa, and Chart. Those are the examples that I use in this presentation. Now, a lot of these telescopes are made with cheaper materials, so cardboard, tinfoil, and occasionally sheet metal, or in other cases, more bare bones telescopes are just old satellite TV dishes that have been wired together with a computer. Now, the problem in this case is that with these telescopes, even though you can see even though you can observe radiation or radiation is in radio waves, you can't exactly figure. It's a bit hard to know that the direction that you're pointing it in, and that can be a problem if you're trying to collect real viable scientific data. Now, to that end, a lot of these telescopes, the cheaper ones, don't really have any solution for that, even though some of them can be positioned, but for the most part, there's no real way to find the direction. Now, there are now the more expensive telescopes, such as the ones used by the Gavitt program, those have guidance systems. Although in that case specifically, it's a it's also a multi-million-dollar instrument, and not a lot of people have the kind of money to use a multi-million-dollar instrument. And so, because of that, I decided to make this sort of my spring semester project, because that way it would be possible to make a very cheap and efficient way for amateur astronomers to figure out what direction they're pointing at. Now, the goal of this whole project was to design a guidance system for chart to identify where it's pointing in three different coordinate systems: altitude, azimuth, galactic coordinates, and right ascension declination coordinates. The aim with including all these three coordinate systems in this case is just to make it more accessible to amateur astronomers, and as well as incorporate some of those coordinate systems that are used by astronomers to uh, base to point to the locations of the objects that they're observing. And that way, there's a way to take what's being observed through the telescope and putting that on a uh, onto the same sort of coordinates that real scientists use, or not real scientists, but people who work in observatories, astronomers, and others who support that role. Now, the methodology that I used in order to come up with this guidance system is that so the position of the radio of the horn itself, which was pictured in the poster, that's using a 9 degrees of freedom spark inertial measurement unit that's connected to a laptop. Now that inertial measurement unit, it's going to relay acceleration position data through the to that computer, and this data will be turned into coordinates using the Arduino IDE. Now, using that by IDE, well, using Arduino software. Now, as far as that software goes, it'll calculate the position, and then that'll be displayed then on the computer screen. And then using that, you'll be able to, the goal is to figure out where exactly it's pointing. Now, in this slide, I have a diagram showing how exactly the methods used behind it, or used behind this guidance system that I've been working on, and the actual Arduino IDE. Internal development interface is what IDE means, by the way. I should have mentioned that earlier. Sorry. But I included that screenshot there just to show that how it's going to work. So whatever the actual coordinates would be displayed in the black part of the window, or the serial port, and using that you'd be able to derive you'd be able to get the coordinates of whatever object you're looking at, if you're, or not object, position of you're looking at. Now, as far as future goals, I do plan on building this thing. The reason why there wasn't a physical prototype included in this presentation was there was an issue with procurement last semester, but as I continue through my undergraduate degree, I do plan on working on this a bit further, specifically developing and actually testing this guidance system in actuality. And in addition, I also plan on allowing a star finding feature on developing that for the telescope to actually see whatever it's, or to, so that if you are looking for a specific object, you can actually find it without having to use a star chart and then the coordinates and manually doing that. Now, finally, there's also some other goals that I have for this system, that specifically reducing its complexity, because currently, so far, it's just the power that's going to be needed for this guidance system that's being supplied through a laptop, or that's the initial plan. And laptops can be a bit cumbersome, and the issue with that is that there's also wear and tear that may hurt performance. So the goal is to replace that with a power supply. And then another thing with the laptop is that the laptop does a lot of other things besides display coordinates. And in order to make the system more compact, the goal is to include an LCD screen there. And then finally, of course, actually having a case for all of this, so that way when it's mounted to the waveguide chart, it won't be exposed to the elements and it won't suffer from any damage to moisture and anything else. And this slide contains we're excited, but If anyone has any questions, I'd love to answer them.
A question on the IMU. What is its accuracy in the 3 axis or repeatability?
Accuracy as in precision, or?
Yes, as a first way of addressing it.
So as far as accuracy goes, I haven't gotten around to actually building a prototype, so I haven't been able to measure that parameter. But as far as inertial measurement units go, they do drift occasionally. That may be an issue going forward with this design. But whether or not that'll be an issue remains to be seen.
All right, and the other side of that question, what is its resolution?
Resolution, that part hasn't been fleshed out as well. But the goal is probably to have it somewhere more reasonable, as in within 1 or 2 decimal places.
If I've looked at a few of these things as a possibility, and I believe what I have seen is, depending on the IMU, the resolution is anywhere from about 8-bit to about 12 or 14. I think 14 is the highest resolution that I've seen. So, you know, you're talking maybe a couple of arc minutes for the resolution.
Which is getting pretty impressive.
Yeah. And as a comment for you, I know that I've seen papers online where they have merged the data from the accelerometer with the gyro that's on the chip. And by combining that data, they are able to increase the accuracy of the measurement. They can use one to kind of cancel out the noise from the other, and therefore they end up with a better first measurement. And so you're starting to actually get close to arc minute, for a more accurate arc minute than having it bounce around with the noise from just one of the 2 sensors. So I'll be interested to see your work.
Well, I hadn't really looked at into that part of things, but if you would be able to send me those, I'd really appreciate it. Some of the papers, at least.
Okay, I'll see if I can find some of those.